We are very used to plotting functions in two-dimensional space, and so we have a pretty good sense how functions appear, roughly speaking, what kind of shape they have. When we think about 3D functions, it's a little bit harder to visualize because our brain is not used to trying to push things beyond 2 dimensions in mathematics. So in this lesson, we're going to take a look at what we call cross-sections and contours. And the idea here is that if we can't visualize functions in 3 dimensions, then how about we find a way to take a 3-dimensional function and visualize it in 2 space. So 3 space means 3 dimensions, 2 space is 2 dimensions. The graphs of functions in 3 dimensions are often called surfaces. Okay, that's just the 3-dimensional name, or the name for a 3-dimensional function on a graph. So there are really 3 kinds of ways we can deconstruct a surface into 2 space. And this involves kind of slicing them in one of 3 different ways. The first is that we choose a value of z and we fix that level of z and look at the relationship between x and y for that particular value of z. The picture that we get are graphs of what we call level curves. We'll take a look at this pretty soon here. These are also known as contours. And those mean the same thing. We'll take a look at the contours or the level curves. So you might have seen this before when you look at a topographical map of a physical region, of maybe a mountainous region, and different shadings and indicate different elevations. And there are usually little contour rings that show you, hey, the elevation is 3,000 feet along this contour. We can also do the same thing for x and y. We can let x be a constant and analyze the resulting curves. These are the curves resulting from slicing parallel to the YZ plane. We'll see this in a moment. And then we could also slice in holding y constant and looking at the relationship between x and z. So we're holding one thing constant, which means that one of our axes is not needed when we hold a value of that axis as a constant. So this is just the overview of it, but before we begin looking at these different cross sections, let's look at 3, and it's not important here that we have x equals 2. This could be for any x value, but I'm just going to demonstrate 3 different surfaces and talk about why these produce the graphs they do. Now these are going to be called planes because they're not going to have any curvature. They're going to be completely flat. This first surface right here is a graph of x equals 2. Okay, this is x equals 2. Well, first of all, we have the x-axis, we have the y-axis, the green one, and the blue axis, which is the z-axis. These are generated in geogebra.org/3D. I'll pull that up in a second to demonstrate this better. And we're saying that this is the graph of x equals 2. Well, why is that the case? Why is it a vertical plane? This is a vertical plane because it goes up and down. And the reason it's x equals 2 is, first of all, we see that that plane does go through x equals 2. In fact, if we just investigate the intersection of this plane with the xy plane, right? The xy plane is sort of this shaded gray area. We're kind of above water, if you will, if you kind of imagine the gray to be the water level, and then we're below water whenever we look beneath that gray surface. And anywhere along here, if we just investigate, for example, this point, well, that is 2 units from the origin in the x direction. It's 0 units back or forth, if you will, and it's 0 units up. And the question we have to ask ourselves is, does that satisfy the statement that x equals 2? Well, yeah, it does, right? Because didn't specify, this function doesn't specify what y and z can or cannot be. It just says x equals 2. So if we pick, say, this point over here, which I'm trying to make look like it's 7 units, oh, sorry, 2 units, but for y equals 7. So that's still 2 units in the x direction. Then it's 7 units in the y direction, and it's 0 units up or down. Now, it didn't say that y can't be 7 or that z can't be 0. It just says x equals 2. So that point still satisfies the statement x equals 2. Now let's pick something like maybe on this edge. Of course, this plane goes infinitely long in both directions, but for the sake of visual clarity, it looks like it's just a sheet of paper. And let's say we pick this point right about here. And I'm going to argue that that's 2 units above, that's about that distance right there. It's about 2 units above the xy plane. So let's think about this ordered triple, excuse me. 2 units in x, then we'll say that's about, I don't know, roughly speaking, about -7 units in y. Okay, so 2 units in x, -7 units in y, and then 2 units up. Once again, notice that every point on this plane will have an x value of 2 because it requires to get to this plane that in any instance that we move 2 units in the direction of x. No specification of what y or z can or can't be, and therefore this is the graph of x equals 2. Now, for y equals 2, it's the same idea, except now we move 2 units in the y direction, right? Every single point along this plane requires that we move 2 units in the y direction. And at that point, once y is 2, x can be anything and z can be anything. For example, this point right here, I'll just again pick on the intersection of that plane with the xy plane. That is, in this case, -5 units in the x direction. It is 2 units, right? It goes -5 units this way. Then it goes 2 units in the y direction and 0 units in the z direction. And that satisfies the statement y equals 2. We can make the same argument for any point. Let's say for x equals 2, y equals 2, and then maybe from there, z equals, let's say, 3. So that's the point. 2 units in x, then 2 units in y, and then 3 units in z. Once again, the key here is that in all of these ordered triples, the y value is 2. And therefore, this vertical sheet represents all the positions where y is equal to 2. Now keep in mind, this plane does, again, go on infinitely in all directions, but we just would have a hard time visualizing it if it were just a big blue blob. Now z equals 2 is no different, except it's going to be a horizontal plane. And let's see if we can reason through this. So if our logic is similar, then all the points on this blue surface, on this blue plane, have a z value of 2. Well, let's pick on this point right here since it's the easiest one to see. And by the way, it is splicing through z equals 2. It's just, again, the perspective makes it look like it's coming down at us because of the way this entire graph is kind of tilted down towards the screen. So this point right here is the point 0 units in x, 0 units in y, and 2 units in z. In that case, that's the z-intercept. And then maybe we pick a point that's 3 units away, and maybe 2 units in the y direction, and then a point on this plane would once again be, in this case, 3 units in x, 2 units in y, and 2 units in z. So in all of these triples, z is going to be equal to 2. X and y can be anything they want, and hence we get this horizontal plane. So if we fix x, then we're going to get a vertical plane that is perpendicular to the x-axis. So perpendicular to x-axis. This graph here is going to be perpendicular to y-axis. And the observation we can make here is that this plane is perpendicular to the z-axis. Nice. Okay, so now that we know what horizontal planes look like, let's go ahead and just visualize this in the 3D calculator, geogebra.org/3D. And now we can just say x equals 1, for example. Okay, well there's the graph of x equals 1. If I make it x equals 2, I make it x equals 3, 4, 5, 6, 7. You can just see that we're just shifting that plane. We can also go in the negative direction, negative 1, negative 2, negative 3, negative 4, and we get the same, we get a parallel plane just shifted in one direction or the other. Do the same thing for y equals 0, y equals 1, y equals 2, 3, 4, 5, 6. Could even go negative 1, negative 2, negative 3, negative 4, negative 5, and so on. Z, same thing. We could do z equals 0, in which case that is the xy plane. Z equals 1, z equals 2, z equals 3, negative 1. Now we're below the water level, negative 2, negative 3, and so on. Now the key in visualizing other surfaces that aren't these simple planes is to slice them by either holding x constant, holding y constant, or holding z constant. And that's really what it amounts to. And in our minds, then we can at least construct the two-dimensional representation of a three-dimensional graph, which is pretty cool. So to help us better understand this from a more intuitive basis, when we create these slices, like imagine a three-dimensional apple. You're holding an apple, and you just choose to do a vertical slice of it, and you kind of take a plane and you slice this thing like so. So maybe it looks kind of like this. And now you're going to slice it down through, right about there. And it's going to slice that apple in half. And so what do we see? Well, we see this outline. This is the two-dimensional outline, or what we call the cross-section. This is the cross-section of an apple when it's sliced vertically. Okay, this ring that I'm kind of mapping out, this is what we would see with that kind of cross-section. We could also slice it going this way. We could also slice it this way, right? We could slice it in half by using a horizontal plane, in other words, holding the value of z constant, and you can kind of imagine what that would look like. That would look like almost like a circular ring if we sliced it from horizontally and then looked down upon it. With functions, it's no different. We can slice a 3D surface in one of three basic ways. We hold z constant and we slice it horizontally. So, here we're going to get the shape of that function at the point of the slice. We could hold x constant, so remember perpendicular to the x-axis, and we see here that it actually forms this shape right here. Or we could hold y constant, again a vertical slice perpendicular to the y-axis, and we get a shape that looks kind of like this. Now here, notice that when we hold the value of z constant, this function right here is now just y versus x. It's y versus x. Here when we slice it, for holding a value of x constant, now we're just looking at the y value versus the z value. So we have this z-axis, and then we have this y-axis. And when we hold y constant, we're now just looking at this dimension right here, which is the x, and this component right here, which is the z. So the relationships that we get, this is a xy cross-section. I'm sorry, we usually call this a level surface when you hold z constant. Xy level surface or contour. Here we get a YZ cross-section, which we typically call an X cross-section. And here, when we hold Y constant, we're going to be looking at the XZ plane, and we call this often a Y cross-section. We're holding Y constant. All right, let's go to an actual function that we've seen before. It's the paraboloid, f of xy equals x squared plus y squared. So it looks like a parabola in 3 dimensions. And we could slice this thing one of three ways, right? We could slice it going this way. We could slice it going this way. Or we could even slice it with a plane going this way. Imagine that horizontal plane, and we slice it, and then we look down and we see the outline of the shape. Well, how do we do this? Well, one way is, again, let's do this visually first in GeoGebra. Let's plot f of xy. You could just type in x squared plus y squared, but I'm going to call it by its name. Sometimes this can be a little clunky, but let me try this again. Of xy equals x squared plus y squared. And there's that paraboloid, and we can actually rotate this by clicking and dragging. And now what I'm going to do is I'm going to say, let's say x equals 0. Now, as I begin rotating this, we can kind of imagine what this splice would look like. Okay, and we can also change the color in here. I'm going to change the settings on this splice, make it a little darker. Now, you can almost see it if we make the there we go. Okay, so if I splice it that way, then we see what looks like to be a paraboloid. Right? You can actually see that cutout right there where the red and the blue meet. That shape right there is the shape of a parabola. And no matter where I slice it, if I change this to x equals 1, notice that once again what I get is the shape of a parabola, but that parabola appears to be lifted up a little bit more because we're getting farther outside of that shape. You can see that we get a parabola there. We also get a parabola at x equals 2, but notice that that parabola is a lot higher up. That two-dimensional parabola is shifted up higher than those other parabolas. Now you can kind of see it there as well where that intersection's happening. Let's do the same thing for y. Y equals 2. Now because this thing is perfectly symmetric, it's going to kind of look like the same thing, but just now perpendicular to the y-axis, and y equals 0, and y equals -1. You can again kind of see that those parabolas are just going to shift up. And now let's do the contours. Let's start at z equals 0. Well, when z equals 0, that plane is just touching the bottom of that paraboloid. Let's shift this up a little bit and see what happens. Well, now you can see that if we slice it, and we sliced off that bottom, what we get is something that looks like a circle. And if we do z equals 2, we again get a circle, but because we're slicing it higher and that paraboloid is opening into a larger opening, we get a bigger circular cross-section. And when we do z equals 3, that gets even bigger because now we're slicing it up higher. And you can imagine that when we slice at z equals 5, we'll get a larger circle. So the way you can kind of visualize this is imagine that this is water and you're swimming around inside of this shape. Well, you can only swim around this circle because you're blocked by those edges. So that's visually how we do it. How would we actually construct and be able to grasp those different cross sections when x is, say, -1, 0, and 1? Well, our function is the function f of xy equals x squared plus y squared. So when I let x equal -1, that's going to produce f of -1 comma y. So all I'm doing is plugging in a value for x, but not for y. I get negative 1 squared, which is 1, plus y squared. So in other words, this is just a symbol representing z. I get z equals y squared plus 1. When I let x equal 0, then I'm looking at f of 0 comma y, plugging in 0 for x. That would be 0 plus y squared, or just z equals y squared. When I let x equal positive 1, well, 1 squared is still 1, so it's going to also be 1 plus y squared. And this is the function z equals y squared plus 1. Now don't let the z and the y throw you off, because when I graph that, my axes are just going to be labeled. Instead of x and y, my input is called y, my output is called z. And better yet, I should probably make this let this go into the negative area as well. Okay, so I have y, I have z. And now if I plot this function, z equals y squared plus 1, that's going to be a parabola that has a vertical intercept of 1 and then opens out from there. So it's going to look like this. And this is just for x equals negative 1. Okay, that's this one here. Now let's plot the next surface, but now this is going to be for x equals 0. Well, z equals y squared would just be a parabola that is the same shape but has a vertical intercept of 0, and this is for x equals 0. And then for x equals 1, that's going to be exactly the same parabola as this one here. And this is also for x equals 1. And the reason we see that is because if we come back to this, the shape of the cross-section is the same in both directions, since this paraboloid is symmetric, right? It has symmetry when you slice it down the center. So there's x equals 1, negative 1. That's z equals y squared plus 1. When z equals positive 1, well, notice that's the same thing. It's just on the other side of the y-axis. It's for x equals positive 1 instead of x equals negative 1. So we could produce those graphs and say, you know, for example, let's say this represents profit or something like that. Well, maybe I want to hold the quantity of one product constant and analyze the profit just with respect to the other product that I'm selling, allow that to vary and see the relationship between that. Now here we can do the same thing, but for y equals negative 1, 0, and 1. So let y equal negative 1. So f of x comma negative 1, holding y constant, will give me x squared plus 1. When we let y equal 0, we'll have f of x 0 equals positive 1. X squared is equal to x squared plus 0. And when y equals 1, we get f of x1 equals x squared plus 1. Now it's going to produce the same graph as we had up here. Again, because of the symmetry, whether you hold x constant or y constant, you're still going to get these three separate curves. So I'll just kind of quickly sketch them here. This will be for x equals, or y equals 0. And then we'll have another parabola here. It's the same parabola. This will be both for y equals negative 1 and for y equals 1. So it's going to be the exact same parabola in both cases. Now lastly, let's take a look at what happens when we hold z constant. When we hold z constant and look at the relationship between x and y, First of all, let's remember that this is the same thing as z equals x squared plus y squared. And when we plug in -1 for z, we get -1 equals x squared plus y squared. And when we let z equal 0, we get 0 equals x squared plus y squared. And when we let z equal 1, we get 1 equals x squared plus y squared. Now what I will say is that if we remember some things from algebra, which this may be something we've forgotten, x squared plus y squared equals r squared is a circle of radius r. Now, in this case, what's this going to produce? Well, you can't have a negative radius. You can't have a negative. So for z equals -1, let me actually go to Desmos for a moment here. And let's plot the function -1 equals x squared plus y squared. The reason I can do this in Desmos is because this is a two-dimensional graph. Now you see that it doesn't graph anything, and that's because there are no values of x and y that you can square and add together and get -1. When you square something, you're always going to get a positive number. So this actually doesn't produce a graph at all. When you plot 0 equals x squared plus y squared, well, that's a circle of radius 0, and therefore it's just going to be a dot. When you plot 1 equals x squared plus y squared, now you're going to have a circle of radius 2, and let's say we plotted 2 equals x squared plus y squared. Now this is going to be a circle that actually has a radius of 1.414, because the square root of 2 is 1.414. So it's the square root of this value that represents the radius. Plot 3 equals x squared plus y squared. We get another circle, radius 1.7. 4 equals x squared plus y squared. We get a circle of radius 2. So here we have I've just copied and pasted the graph. I'll put that z equals 0 in there. This was z equals 1. This was z equals 2, z equals 3, and z equals 4. For -1, there are no points, x and y, because, again, that argument that you can't square two values and add them together and get -1. So there are no real solutions to this. And so this is exactly what we saw when we considered our graph in GeoGebra 3D. And so we'll just plot f of x, y equals x squared plus y squared. And then when we plot z equals -1, well, we can see that that actually does not ever intersect with our surface. And that's why we don't get any points. We don't get anything at all when we use z equals -1. When we do z equals 0, we've already kind of mentioned this, but that just basically touches that point, the bottom of that paraboloid. And so it's just a point, as we see in our contour plot here, or our level surfaces plot. If I make z equal to 1, we get that circle of radius 1. Z equals 2, circle of radius 1.414, circle of radius 1.7, circle of radius 2. This is a nice place for us to stop the video, and in the next video we'll actually analyze a real-world surface and try to think about, what does this really tell us about the data, and what does it tell us about the model?